So, Dr. Alexandre Cardaillac, I hope I've pronounced that okay, is a Postdoctoral Research Associate in the Underwater Computational Imaging cluster at the University of Sydney, and he's part of various research hubs in the marine robotics group specifically. Alexandre has had a really interesting sort of pathway, taking a Bachelor of Information Technology at Nantes, and then an MSc in Artificial Intelligence from Heriot Watt in Glasgow, Edinburgh, and then completing a PhD with the Department of Marine Technology at the Norwegian University of Science and Technology. So it's already an interesting set of moves. His main area of interest, as you probably will gather from tonight, is underwater computational imaging, especially when we can't use vision in some ways, with combining acoustic and optical data. His interests also include situation awareness, and he helps drive underwater robotic systems. He's even brought a little one with him. He's going to tell you about more of that. And he's publishing and working on sort of camera sonar combinations for exploration and other aspects. And Daniela, Dr. Daniela Helbig, trained another interesting trajectory, a degree in physics at the Freie Universität in Berlin, followed by a PhD in the history of science at Harvard. And her various interests include the philosophy of science, and she's probably the world expert, or at least one of the experts on Hans Blumenberg, as well as the history of photography and other technologies of vision. And some of you want to, and she's completing a book at the moment, which is fascinating sounding, on the test pilot and physicist Melita Schiller-Stauffenberg, and she's very interested in aerial surveillance, among other topics. She's published in a range of, many of you might know Daniela, but if you don't, you should. In philosophy, she's written for New German Critique, for the Historical Records of Australian Science, for the history of photography. So I think that range tells you the kind of breadth of her interests. So I'm really delighted you both agreed to do this. I'm going to hand over to you now, Alexandre, and thank you very much.
Thank you. Yes, so thank you very much for having me today and for giving me this opportunity to present as part of this Vision Culture Seminar Series. So today I will talk about what it is to see underwater, but not exactly from human perspective, like how do we perceive the color from the eyes, but more like from the robotic perspectives. So using cameras or other sort of sensors, and how can we use them to understand the underwater world. So first of all, importantly, why do we actually need to see underwater? And I think there are three major reasons that I think of for now. There's of course many of them, but three of them are particularly important in my mind. First is, of course, we all are curious. We want to see what is down there, what is in this ocean. Like, who's never been to the beach and look at the ocean and at the horizon and think, what is down there? What could we explore and find out down there? And as a matter of fact, for millennia, this curiosity has driven exploration and discoveries about marine life, geology, but also the ecosystems that are alive in these oceans. And interestingly, it's actually still, most of the oceans are still considered unexplored, and it's considered as one of the least understood region of the Earth. So the second reason why we actually need to see underwater is to understand environmental impacts. First of all, because the oceans are the ecological region most critical to support life and natural habitats. For example, we can find the coral reefs and how they evolved with time and how humans can impact those environmental clusters. So it's really important to drive technology and to improve the knowledge of the deep sea so that we can understand how we can better conserve them, but also understand them. The last point is about the societal impact, but in this slide I sort of focus more on archaeology, because a lot of artifacts from ancient civilization and cultures are actually underwater because of some event that could have happened. So, for example, if you inspect the coastlines of many countries, you're very likely to find wrecks from previous civilizations that could indicate some societal impact. And this actually also helps understand the interactions, the previous interactions between the humans and the maritime environment. So, for example, I have a few pictures here. On the top left, these are actually Roman ruins that are now underwater, and the discoveries of these help understand how Romans used to party, for example. But you could think the same way for shipwrecks. For example, in Norway, we find Viking ships that can help understand what sort of technology they had access to navigate on the seas. And so this sort of part is really important to reveal how humans used to interact with the maritime environment. So now that we know what we need to see underwater, we now need to look at why it is actually hard to see underwater. Because you might see online a lot of pretty pictures and you might think it's not that hard to see underwater, it's there all clear, always beautiful colors and everything. But the reality is, it is quite challenging to see underwater, and there are a lot of different effects that make it hard to capture good images. So I have here the three main sources of visibility reduction, and most importantly, it's important to remember that vision is degraded due to light effects caused by the underwater environments. The first one is about absorption, meaning that as the light goes through water, it kind of loses the wavelength energy, meaning that the colors become distorted. And for example, you can see on the right, there is actually something behind, but it's hard to see. You can only see it once you get closer. And the second part is scattering, which describes how light bounces on an object and come back to our eyes to see it. Well, underwater, it's a bit more difficult because it actually bounces everywhere in the water before going back to the camera, which adds some more degradation to the imagery. So all of these effects, they make the images look not so contrasted, but also blurred. And finally, we have marine snow, which are all the little particles that we can find in the water that here appear sort of white, that sort of increase the previous effects. So if we look a bit more closely to light absorption, we can see that it absorbs different wavelengths, but at different rates, which means that, for example, you will have some colors that are distorted much more, absorbed much more quickly than others. So on the video on the bottom right, this is a color palette, and a diver is holding it and going deeper and deeper, and you will see how the colors change over time and over depth. And on the top right of the video, this is the image close to the surface, so with the correct colors. And as you can see, as you go deeper, first you lose the red part of the colors, and then a sort of purple and yellow green. And what's also important to note here is it's not always the same in every oceans. Every oceans absorb light differently. For example, in oceans, in open oceans, you might still have some light at 200 meters depth, but on coastal waters, very often, even after 20 meters, no light, no more colors. So light absorption is important to consider here. And this is also why everything sort of appears blue underwater. For example, on the coastline of New Zealand, there are these sort of bits of mussels, and they completely look blue when you just take an image without anything on top of this. I also added these pictures on the bottom right because it makes it really possible to see how distance to a camera the color changes. So the closer to the bottom it is, the closer to the camera, and it's sort of the most white part of the image. And as you get further, it becomes more blue and blue until it's completely dark, and it's not possible to see anything because the light is completely absorbed. And as I said, the suspended particulate matter really increases the attenuation effect of the light. And it also absorbs different wavelengths, for example, the blue light, which is why sometimes some of the oceans or seas appear more green because they have more phytoplankton in these kind of regions. And interestingly, now there is this map of depth of the oceans based on how the sunlight travels in the oceans. So close to the surface, you would have the sunlight zone because it's relatively close to the sun, followed by twilight, and finally the midnight zone because there is no more light at all after 1,000 meter depths. So the second part is about the light scattering. As I said, the light scattering is about how the light bounces until it reaches either the eye or the camera in our case. And it's important to note that if we look at the graph here, we have the light from the sun. Ideally, it would reach the object here and come back to the camera. In this case, it's all good, no worries, if we forget about the absorption. But what happens is because of all the particles or molecules in the water, very often the light bounces on something in the water and back to the camera, which make it the image on the left look hazy or blurry, which have this sort of fog effect, which can make it difficult to really see at distance underwater. So, luckily, because there's all these sort of effects, we also need to find a way to quantify them so that we can use them to our advantage to restore imagery or understand how we can overcome these issues. And there's this guy, Nils Gunnar Jarlov, which was a Sweden oceanographer and researcher. He spent his life on ocean optics, and he developed this classification scheme about water bodies based on optical properties, so based on how they look. And so in the 40s, he was on this expedition called the Albatross, and they went during, I believe, 18 months all around the world and collected samples in many seas and oceans. And based on this, they made this sort of map where they categorize on each part of the map how the ocean behaves with light. And because of this, this classification scheme is still used today to simulate oceans or really understand how we can see in specific type of oceans. So, so I have actually the map here. So he actually traveled in most places to really derive this understanding of light interaction with the water. So, now that we know what are the issues on the water, we need to look at how to actually overcome these issues and address them. But more particularly, how can we overcome the lack of natural light underwater? You might be tempted to say, well, if it's dark, just add a light close to the camera and that will do the job. But it's a bit more tricky than this, especially because of what I said before, this scattering effect, meaning the light might bounce everywhere. So this video is actually a video that I took with my robot 2 years ago when I was inspecting a ship in a Norwegian harbor. And naively, I was also like, I just put a light and activate turn on fully the light. And only half an hour later, I realized that, well, we don't see anything. It's hard to use. I completely lost my time with this. So, because it's kind of difficult to see, but you can sort of see there's like orange shape behind, there's something. So it's really important to use the light in a smart way. It's not just about turning on and off the light. So the first thing that we can do is placing the light in a specific way relative to the camera, so that we can minimize the light path overlap, which means there's specific light paths that go from an object to the camera, but there might also be a light path from the light to the object to the camera. And if you minimize this overlap, you can sort of reduce all these particle effects that you can see in this video. And so it's a very convenient approach, but it would require to be able to actually move a camera and a light at the same time, which can be very difficult with using robotic solutions underwater, because it's hard to design and hard to develop. So the other solution would be to just have this long vehicle. You have a camera and then lights that are sort of placed far away from the camera. And what is happening here is that there are actually strobes that are flashing at the same time as the camera is capturing images. And by doing so, because the strobes are strong enough, it also removes the absorption effect, so it restores the color only locally. And it can also, in some scenarios, have the strobes that has a specific color when light is being absorbed in specific wavelengths. And so I think, so in this image, I like this image because you can actually clearly see the light beam going and reaching the seafloor and completely restoring the colors of the seafloor when the camera is capturing the image. So when you do so over time, you can collect all sorts of imagery that make it possible to document either seafloors or inspect any underwater natural assets. The second possibility is not to use a regular camera, but what we call a hyperspectral imager, which collects reflectance, or more like collecting the whole spectral profile of objects. And when you do so, you actually obtain each reflected wavelength of an object. And because this super guy Nils Gunnar from before collected tons of data about the oceans, we can now sort of understand how we can correct the spectral imagery to obtain better images. And then we can obtain, as you can see on the right, sort of sections on the seafloor with all the sediments segmented and so on. And so this has really applications in archaeology, but also in understanding how the seafloor is formed and evolving with time. So finally, how we can overcome this issue? Using computer edit corrections, which means it's not because you have a bad image that it's over. There's still some hope. There's still solutions to restore the image to obtain true colors. And to do this, as you can see on the top left, it's the original image, and on the bottom left, it's after the color correction. And if you look at the color palette, you can see that the red part of the palette is actually restored, which is a good thing, meaning that we can now find solutions even after operations to restore the colors. Traditionally, this is done using what we call markers, so we identify specific part of the image, and based on this, we restore all the colors. But nowadays, with the imaging technologies of AI and deep learning, it becomes possible to just send through images to a model, and it will come back clean. So this is good, but we still are very limited with distance. It's hard to see more than a few meters away. So maybe, what if hearing was actually a better way to see underwater? So for this, and it's actually extremely popular in the underwater robotics communities, we use what we call acoustic sensors, which actually send acoustic beams in an environment, and by listening to the echoes, we can know where are the objects around. So if you look at the videos on the top right, we can see the robot is sending beams a bit everywhere, and from this we can derive an image. So, for example, on the bottom right, this is a plane that was crashed in the ocean, but this way, using sonars, acoustic sensors, we can find from very far away, hundreds of meters away, wrecks or any sort of point of interest. So, personally, I believe that acoustic is really the future of underwater robotics, but it can be sometimes ambiguous because it sounds and not just light. Sometimes the echoes can be tricky to understand, and you could think this specific echo could correspond to something, but it could be something completely different just because maybe it echoes everywhere from the surface and back. So, but it is an exciting field to work in. So, yes, that's, I believe, 20 minutes. So
Thank you, Alexandre. You're going to show what
yes,
your...
but I have a little something to show. I did not come empty-handed, and actually brought one of them, one of the robots that we have in the lab. So this one is actually a miniature version. So it's not like autonomous. Technically, it should have a cable that connects it to the shore, and someone is controlling it. That's what we call a remotely operated vehicle. And what's good with this one is actually there are 4 lights on the side that are separated from the cameras that are below here on the side. And we have 2 of them so that we can sort of replicate the eyes. We also have 2 so that we can perceive the depth. And in the middle, we have the hyperspectral imager that I just shown before as well. And yeah.
Thank you, Alexandre. I'm going to ask Daniela to respond. Don't worry, you can keep your questions about AI, about hearing being better than seeing, all of that. We're going to get to it. Daniela.
Cool, thank you. And thanks, Mark and Nick. It's fun to be part of this experimental dialogue. And to Alexandre, fascinating work by your group. So there'll be plenty to talk about. I made this very, very difficult decision. It was difficult in this brief response to focus on the seeing part and to try and tease out some connections between what we mean by seeing and this question of, vision cultures, rather than underwater, which I hope we get to in the discussion. And the reason for that is that I wish to, in a completely unfounded way, put forward a wild thesis that we're about to see a new era of new interactions of these vision cultures. So I want to give you a historical backdrop that hopefully makes you see why I think that. Yes. I want to tease out this, which, reading a bit of Alexandre's work, I would also think, yes, that's the way to go. Hearing is a way of seeing, right? We actually have sound waves that we throw at these objects. We analyze what comes back from these sound waves, and that magic happens, right? Because then we've got a picture suddenly on the screen, and now we're all happily looking at this picture, which uses electromagnetic waves, right, to communicate with our eyes, saying, oh, now we can see that thing. So it's magic and cheating, right? And something we're all too familiar with. This sounds very cool, but the principle is very similar to when we go and get an ultrasound. We don't even think twice. When we look at the screen, we ignore the gel and we see, our insides, right? This is the paradox that is sort of crucial for us here, right? That process of making this visible has become invisible. We just think, oh yeah, fine, here's how we see. And that's the one I want to focus on, because if we want to think about, shared cultures of vision, that's the one that interests us. So I want to give the very briefest historical backdrop to say, who were the people to whom exactly this question, How do we go from something non-visible to the visible? Who are the people for whom this became, a shared problem? About 100 years ago, these were mainly a bunch of scientists, artists, and also writers. But they speak to this question, what do we mean by those vision cultures? The people who got interested in this paradox that now we tend to just, not see. And here's an example. Philosopher. We're in 1936 in Vienna with Moritz Schlick. He gets murdered the next month, but let's leave that aside. And here's what Moritz Schlick says. He asks you to imagine this sort of surgically created semi-monster, where he says, imagine this creature, human-like creature, where we connect the optic nerves to the ear, and we connect the auditory nerve to the eye. And now he says, what do you get? You can hear all light impressions as sounds, and you can see tonal impressions. So you can listen to the painting, and you can see the music. So this imaginary creature of this philosopher is perfect for our underwater thing, right? Because that creature can see that ship. Can't hear it, but can see it. But the point is that Schlick had to imagine that. That sort of in 1936, we didn't have our magic cheating technologies yet, but he really had to worry about what's going on with his senses there. And that's my point in going back to this gang of people, because they had to ask this question and say, what does this mean? And what do we do with it? And there's, of course, a reason why they're all so obsessed with it. Really many people obsessed. And again, I'm going to demonstrate this with another picture over here. An 1896 picture of, now we easily say, that's a hand on an X-ray photograph. So that's 1 year after X-rays sort of get discovered, if we want to use such a word. And again, we now look at this hand, and it's kind of straightforward for us to say what we don't see a hand, right? We see a hand that has been made transparent by sending X-rays through it. And what we see then, these dark shapes, the bones, that's where the X-rays didn't get through and didn't land on the photographic plate. And we see the rest, where they made it through. Another obvious example of if we pause to think about this, we say, yes, that's what we see. But we don't pause. We just look at this hand and say, yeah, can see that. So that's the moment that got the people I'm talking about worked up. And that's why it's helpful to look there when we want to think about shared sort of cultures of vision. Those years around 1900, it's one of those big around 1900 periods where you get two things at once. You get encounters with physical reality that is simply beyond direct sense perception, like X-rays, electrons, you name it, and it just gets worse as we come to the turn of the 20th century. And at the same time, we get these ways of seeing, like this X-ray photograph, that are mediated by these scientific discoveries and technologies, and they become much more commonplace. People see this more and we can get used to this immediacy of seeing. So we've got this back and forth between figuring out how the hell to see something really tiny and using this as new ways of seeing. And that creates what I think we can really call these intersecting cultures of visions, where you've got a shared active interest between completely different people with completely different questions in this kind of process of vision and in these mediated ways of seeing that still look like a problem rather than something we just take for granted. That's just one of many examples that you could put up to say, well, what do we actually mean by these shared interests? We could say, the reality or the constitution of the object being seen. So for a philosopher like Schlick, there's a real realism question here. Not so much for the bones in a hand, we've seen skeletons, but for any kind of submicroscopic entity, people had no idea, and we still have no idea, to what extent, an instrumental extension of the senses gives us any kind of good picture of that submicroscopic reality. So for many philosophers of science, scientists, that was the daunting question, what the hell is there now that we can't see it? But of course, other people asked other questions. So I picked one of the most famous examples from art history to point that out. Here you've got Claude Monet and his haystack series. Why on earth would you go and paint, famously, the same haystacks 30 times over the course of 5 years? every time in different light, under, a different time of year, all of those things. Not because you have a doubt that there's a haystack, even though Kandinsky got really angry with him because he couldn't make out the haystack, but that's also besides the point. But because you want to question this same process of, so what's that link between seeing and representation here, and to what extent are these completely changing conditions, every day is different, actually constitutive of that haystack? So there's another very real question about what does this continuously changing way of ever perceiving the same object mean? What would it mean to separate those things? And if we want to be just a little bit anachronistic, we can add a third one here, right? So not quite the same century, but here's yet another question that we can pose, right? I can come and I want to investigate this ship's hull, not because I have doubts whether there's a ship at all, or not because I'm particularly interested in asking what it means for this ship to be bluish and blurry, but because I want to know whether there's a hole in the hull or whether something got dropped from it. So that's a third question that is completely different from the other two, but partakes in the same active interest in bringing out this process of seeing rather than burying it. One more example before I put forward my steep thesis. Half a generation later, another super famous episode from the history of art, right? Art does not display the visible, it makes visible. Paul Klee, talking here about graphic elements, about points and lines and how you use them to actually display movement. But what's interesting for us in this context is that Klee too, which is often forgotten, comes straight out of this context of being very interested in scientific realities having been proved to be, empty, not there, mainly not visible. In the same text, he points out that the reality of visible things is it has been laid bare. So that goes to these scientific insights. The visible in relation to the entirety of the world is an isolated example. So Klee was very specific, and this little drawing here speaks to that. It says making visible, and you've got this almost like lab machinery with which the artist works, and Klee construes the artist's task as parallel to the scientist's, as a process of labor in which you make the invisible visible, along those lines, not some inventive or authorial process, but this active work of making visible the non-visible. And there's one tiny important bit of context to this that I can't leave out, which is that where did he actually come up with this idea? This is forgotten almost more often than this scientific point. The first time he mentions this idea about the role of art, of making the invisible visible, is when he's writing in his diary in the First World War at a military aviation airbase, and his job is to watch crashing planes and draw them and empty them. So two things come out of this for Klee from this job. One is this big theoretical commitment here, and the other thing, this element of the arrow enters his paintings that both brings, the idea of, movement, of crashing, of bombardment. They all get absorbed with those arrows. But also, of course, if you will, he's also placing, what changed his ideas about vision in another extreme environment. You cannot be up in the air as a human without technological mediation. And that brings a whole lot of other associations with this, not least that aviation, just like, underwater exploration, lives in this space of ambiguity between, yes, curiosity, exploration, the attempt to put ourselves in places where we can see differently and where we can see other things. But it also brings context like the facts that usually what gives us the tools to exist in those places are military applications. Sonar, the basis for what you've been talking about, Alexandre, has its root in the First World War in, submarine mutual detection. So this context gives us a whole batch of important ambiguities to think about what are and who are those visual cultures. And I think raises a bunch of nice questions in closing for where we are today. Because while that period is, a remote period, what we've got today are a whole lot of engineers who are also constructing pictures all the time, right? We can debate about, you know, those images and Monet and what he made of his haystacks, right? But my point is that a lot of the images that are the most relevant in science now are these engineered images, produced images that do not aim, just like Clay said, to be any way of a mimetic representation. Who knows what it looks like there underwater, but that are made objects that now fulfill a really important epistemic function, but at the same time, they build a whole new bridge to artists who also, you know, take it to be their task to produce something that, you know, changes. So there is a new intersection, I would think, of visual cultures that is currently just forming, and to which probably this series speaks in precisely this sense. So that's my historical backdrop, and I hope now we can come back to putting all of this underwater.
Thank you so much.